Hi, my name is Robbie Tong, and this is my electronics project portfolio. So this is one of the first projects that I made in school. For CPE-233, we implemented a RISC processor on an FPGA. Here you can see the coordinates of the ball going on the LED display. We use the Nexus 2 um, Digilant board development kit. So all this that you're seeing was written in assembly um, using instructions that we implemented in hardware and VHDL on our soft processor using VHDL. The object of the game is to trap the ball, and that was my final project for this class. Here this is my Xilinx setup. I quickly switch over because that apparently the VHDL is not interesting. The software is more important at this point. I think the software was more important at this point because I had worked so long on it. I used all the registers and no RAM. I was kind of in a rush and I didn't want to switch up my workflow. Here's the endless label statements. It's also worth noting that I designed the PS2 keyboard driver because the original keyboard driver that our teacher was using was not sensitive enough. I came up with a simple design. It's a shift register. That's all it is, a shift register. And the PS2 clock protocol, all it does is it clocks on falling edges when it has data. So when it has data, it starts clocking one of its pins. So on each clock, I have the shift register take in data, and once it stops, you have a keyboard code. So my driver raises an interrupt flag, and the processor jumps to .org3ff and does its interrupt routine. So this is one of my most recent projects. The goal was to figure out how to actuate electronically a shutter release cable for a vintage camera. The client wanted this shutter release cable to be triggered with a timer. So the device would count down and then this would actuate on this shutter release that you see right here. So the goal was to combine this shutter release and a flash housing into one package. I thought this would be a good choice because it can fit on top of the camera. And with a servo, with a microprocessor, perform all these tasks. And so here I use a hinge to attach the servo to the top, and here's the build process with the LCD screen. You can see. And here's a video of the prototype.
It's all hooked up. Alright, so the first thing, I guess we go test, and then down to trigger. Cool. Alright.
This is my mini POV, and the thing that makes my POV different than all the other, DIY persistence of vision toys out there is that the pattern it flashes is stored and reprogrammable. You can send different patterns by screen programming. So I wrote a Java application that flashes a portion of a desktop screen or a laptop screen, and it flashes it black and white, and by doing this you can transfer the pattern to the device. Okay, so I'd like to talk about my Android application. It's a resistor calculator that figures out particular combinations of resistors that the user enters to achieve a particular value. So right here we have a particular combination, and you can drag it around. It's cute. So when you click on a particular resistor, we can change the value. So instead of it being 11.7K, you can see that up there, let's add one more K to it. So we can change this, and let's use red and then press the K button. Done. So now it increased. You can see, you can perform a Monte Carlo analysis on the random distribution of all the components. So you can see, you can look, you can expect where the spread of your combination is going to be. In our case, it's going to be pretty large. So, calculating a 1%, like expecting it to be the value that it calculates is pretty unlikely. So below you can see the percent error, and the green bars represent the standard deviation. So this is the inventory tab. So it takes into account quantity. So these values right here, that just the text, are values that we already that are saved. So if the user wants to save something, this is that. So let's calculate something that we don't have. Let's calculate 55 ohms. Well, let's calculate 88 ohms. So this is 88, used a 100 ohm. Let's play with it and say that we don't have any 100 ohms. Okay, so it just made one in parallel. Let's tell it we don't have any 180 ohms. I would like to see what happens. Okay, so it's just putting them in parallel. Some other interesting ones. Yeah, so this one's pretty interesting because then you can see like the algorithm calculating, different branches and combinations. This one's a little more tricky. Yeah, so my program rotates. It attempts to fit components within the screen width. It also does capacitors. Does it in the same way it does resistors. I mean, like, adding is just parallel, and then series is an inverse sum. Okay, so this is one of the projects that I made at my internship at Maxim Integrated for the Embedded Power Measurement Group. I was an applications engineering intern, and I designed this programmer to program Maxim's line of 78XXX family chips. So these are AC power measurement reference designs, and they communicate over SPI, like a SPI PMOD standard. The code is read from an SD card up here, and the Arduino is the main controller. The power is completely isolated. These are ADAM signal isolators, and this is a CUI 5-volt isolator. It's a pretty thick chip, and then even the programming button is isolated. There's an FTDI over here, This was my design. It was designed in KiCad. Let's see the Maxim integrated swag. And yeah, a video of it programming it will follow. Green means that it programs successfully. And when it programs unsuccessfully, it flashes an error code in red.